Welcome to the Electrical and Electronic Engineering Lecture Series. Today we are looking at the Engineering Lecture Series Self-Test 11. Your anchor person is Professor Michael C. Ndinechi. The topics we are going to cover in this Self-Test 11 are oscillators, feedback oscillators, and relaxation oscillators. If you go to the engineering lecture series, you will see these topic oscillators in module 046, the feedback oscillators in module 047, and a relaxation oscillators in module 048. Follow us in this engineering lecture series by subscribing to my YouTube channel at https://youtube.com/@NdinechiMichael.c. Please like, share, and drop your comments in the comment section. Like we have said, to learn more about the topics that we are having the self-test on, you can look them up using the links provided. Thank you for being part of the engineering lecture series. Now we start with our question 1. But before then, it is always good, after having series of lectures, for one to go back, ask questions, and see how you can answer them. If you can answer them well, it means that you have understood the lectures. And that is exactly what we are doing here today, to help you understand more and prepare to take up questions in the topics we have covered. It's not going to take us so much time, just about 30 minutes. Question 1 says, what is an oscillator? What are the two classes of oscillators? Differentiate between oscillators, signal generators, function generators, and synthesizers. And we answer A. An oscillator is any electronic circuit that generates an output signal without the necessity of an input signal. The oscillators produce a periodic waveform on its output with only the DC supply voltage as the input. The output voltage can either be sinusoidal or non-sinusoidal. So you can see that the term oscillator is all-encompassing for those devices that can generate output without the necessity of an input, except the DC power supply voltage that powers the circuit. And the output could be a sinusoid or a non-sinusoid, like square wave, sawtooth, rectangular waveform. So it is very important that you know what oscillators mean. Now we have two classes of these oscillators. One is the ones that use feedback circuits, and the other one called the relaxation oscillators. Now, the one with feedback circuit returns a fraction of the output signal to the input with no net phase shift, thereby resulting in a reinforcement of the output signal. When we say no net phase shift, It means that there is no reversal of phase, that it is exactly the signal that comes out of the output that is fed back, that the phase is the same, must remain the same for it to aid the input and improve the next output. Now, after oscillation have started, the loop gain is maintained at unity, that is at 1, to retain oscillation. If the net gain changes, it is either the oscillation decreases or increases, thereby leading to distortions. So the loop gain must be maintained at unity to retain oscillation. A feedback oscillator consists of an amplifier for gain and a positive feedback circuit that produces phase shift and provides attenuation. Now, what we are saying here is that when this feedback comes, even if it is coming with a phase shift, then there will be an amplifier that will correct that phase shift. Now, we say that for oscillation to start and be sustained, the loop gain must be at unity. When this signal is being amplified, then the gain of this amplifier must provide some attenuation to maintain subsequent outputs that are ordinarily supposed to be amplified by the amplifier to remain constant. So it is important for you to note that for the feedback oscillators, the net phase must be equal to 0, so there will be no net phase shift, and the oscillation have to be maintained at unity. That is, the loop gain has to be 1 for oscillation to be sustained or retained. So, the second type of oscillators are the ones that instead of feedback, they use an RC, that is resistor capacitor timing circuit, to generate a waveform that is generally a square wave or other non-sinusoidal waveforms. We say non-sinusoidal waveform to be waveforms like rectangular waveform, sawtooth waveform, and ramp waveforms. Now, it is also important for us to differentiate between the terms we normally use to associate with signal, or waveforms in our electric and electronic circuits. Say that the first term, the oscillator, is usually used for a signal source that generates only sinusoidal waveforms. Before now, in A, we have defined an oscillator as something that produces sinusoid or non-sinusoidal waveforms. But we are now coming closer to their specific meanings. We say that when we use the term oscillator, we usually use it for a signal source that generates only sinusoidal waveforms. The term signal generator is used for signal sources that not only generate sinusoidal waveforms, but can also be used to modulate a signal. That is, in your communication systems, you generate your signal to modulate any signal you want to transmit. So we call that a signal generator. The term function generator is used for instruments that can provide a variety of different shapes, such as sinusoidal, square, pulse trend, rectangular, triangular, and sawtooth waveforms. So, an equipment you call a function generator will be able to generate various different shapes of waveforms. And finally, you have those equipment you call synthesizers. And we say that they are oscillators in which the signal is built up digitally. So the other ones will give you mainly analog signals, but a synthesizer will give you these waveforms in form of digital output. Question 2 say, using a suitable diagram, state and explain the two conditions that must exist for oscillation to take place and be sustained. Mention that briefly, but this is a separate question and can come in any form. Say, for oscillation to occur and be sustained, two conditions must be satisfied. The first condition is that the net phase shift around the feedback loop must be effectively 0 degrees. In other words, there should be no net phase shift in the feedback loop. The second one is that the voltage gain around the closed feedback loop must be equal to 1 or unity, so that there will be no distortions. As we go on, we see some further explanations on that. So you must note this and have it at your fingertips, that for oscillation to occur and be sustained, the two conditions that must be satisfied will be that there will be no net phase shift around the feedback loop, and the voltage gain around this closed feedback loop must be equal to unity. Then we can see that illustration in our next slide. But here, the voltage gain around the closed feedback loop, which is denoted as A subscript CL, is the product of the amplifier gain, AV, and the attenuation of the feedback circuit, beta. Then, mathematically, we can say A closed loop is equal to AV, which is the amplifier gain, multiplied by the attenuation, beta. Attenuation is the opposite of amplification, because attenuation is supposed to reduce the signal strength, or signal amplitude. So it is being attenuated. And if you look at the circuit there, you see that if you look at the amplifier, which has a gain, AV, which represents the oscillating circuit, it gives an output V out. Now, a part of this V out is fed back through the feedback circuit or the feedback loop. Say that in that feedback loop, the phase shift must be equal to 0. If you look at the arrows in black dotted lines, you see the direction of the arrow, that the output is fed back through the feedback circuit. Now, if you look at that signal waveform in red, which is going into the feedback circuit, and the one that is coming out, we have illustrated using this different amplitude. But if you look at that, you see that the phase with which the signal enters the feedback circuit is the phase with which it comes out. But it has reduced in magnitude, showing that the signal is attenuated but remains the same phase. And again, if you look at the second figure there, you see that this signal that is fed back is also being attenuated by a rate known as beta. That is why the amplitude of the signal coming into the feedback circuit and the one coming out are not the same. The one coming out, that is the red waveform, the one coming out is far smaller in terms of the amplitude, showing that there is attenuation that have taken place on that signal that is coming into the feedback loop. So that is the illustration of the two conditions, that the phase shift, net phase shift, must be equal to 0 degrees and there must be an attenuation. So we use this waveform in red to show that the phase with which it entered is the phase with which it comes out, and the magnitude of the signal being fed into the feedback circuit is not equal to the one coming out. The one coming out is smaller because of attenuation. Now, that is what is explained here. If a sinusoidal waveform is the desired output, a loop gain greater than 1, that's we are now answering question C. If a signal waveform is the desired output, a loop gain greater than 1 will rapidly cause the output to saturate at both peaks of the waveform, thereby producing unacceptable distortion. To avoid this, some form of gain control must be used to keep the loop gain at exactly 1 once oscillations have started. For instance, if the attenuation beta of the feedback circuit is 0.01, then the amplifier must have a gain of exactly 100 to overcome this attenuation. Else, the level of distortion that will occur will be unacceptable. Then question 3, say, what are the startup conditions necessary for oscillation to begin? Remember, we said the oscillator does not need any input except the DC supply voltage, which powers the circuit. So then, for it to start to oscillate, certain conditions must be met. So this question is asking us, what are those conditions? And our answer is, for oscillation to begin, the voltage gain around the positive feedback loop must be greater than unity. Remember, we say for oscillation to be sustained, the loop gain should be equal to unity. But we say for it to begin, the feedback loop gain must be greater than unity so that the amplitude of the output can build up to a desired level. We will illustrate it shortly. The gain must then decrease to unity so that the output stays at the desired level of oscillation, and this is now sustained, as we can see illustrated in Fig. 6. From the figure, oscillation starts at time equals T0. The condition at that time is that the closed loop gain is greater than 1, which we said in the first sentence. And this being greater than 1 causes the sinusoidal output voltage amplitude to build up to a desired level. Then, as this closed loop gain decreases to unity, then it comes to unity. When it comes to unity, the amplitude of the output remains the same, and that will now be your oscillation taking place at a desired amplitude. Let us see quickly what is happening. Now, we say that the circuit in 6A is the circuit we have seen. An amplifier has an output. An output, part of the output is fed back to the amplifier through a feedback loop. And this feedback loop, we have both net phase shift of 0 and attenuation beta. And the closed loop gain will be equal to the amplifier voltage gain times the attenuation beta. Now, look at the second diagram and see what is happening. At time t equals T0, that is, at time equals 0 minutes, the oscillation begins to build up with small amplitude. That small amplitude is fed back because for it to start, we have said that this gain must be greater than 1. So because it is greater than 1, you see the next amplitude of that signal is bigger than the first one. This one is fed back again because it is bigger than the first one. It amplifies because it's greater than 1. So the output becomes next bigger or higher than the previous one. The same thing happens when it is fed back. The amplitude becomes higher than the previous one, and it continues until it gets to the point which we marked, probably T2 now, the next dotted line down, which is the desired amplitude you want to maintain. So we are saying at this point, this system must be self-correcting by retaining the gain at 1. When that gain is retained at unity, then the subsequent amplitudes remain the same. So you now tap from that place, the amplitudes remain the same for your operation, and you have constant amplitude signal that is no longer fluctuating. If you allow the closed loop gain to continue to be greater than 1, the amplitude of this signal will continue to grow until the point it is no longer what you want. Then it introduces distortion. So if you look at it from t equals t naught to that, place, let's call it t1, where you now have the amplitude of what you want, the closed loop gain must be greater than 1. But when it gets to the point where you want, the closed loop gain must be equal to 1 and remain the same. Question 4 says, give 3 examples of RC feedback circuit oscillators and their applications, and B, briefly explain the operation of the lead-lag circuit of the Wien bridge. We quickly answer that 3 types of feedback oscillators that use RC circuits to produce sinusoidal outputs are the Wien bridge oscillator, the 20 oscillator, and the phase shift oscillator. The applications include generation of frequencies that are less than 1 megahertz. When you are looking for low cadence frequencies, you use these circuits to generate that. And the Wien bridge is the most widely used one in this range of frequency generation. That is why in our model we treated this Wien bridge. And the second question now is asking us for us to explain the operation of this Wien bridge oscillator. Operation of the lead-lag circuit of the Wien bridge is used in the positive feedback loop of an operational amplifier, as we can see in the figure. Now, when we say positive feedback, it's positive in the sense that it is feedback to help to improve the strength of the signal that is fed back to the operational amplifier. So when that is done, we say that it is a positive feedback because it is trying to aid the input to the system. Now, for this lead-lag circuit, there is a voltage divider which is used in the negative feedback loop. Remember, your operational amplifier has 2 inputs, which one is called marked positive, the other one is marked negative. One is called the inverting, and the other is called the non-inverting. As we go on, you will get to know these terms more, because in our subsequent lectures, we may be treating operational amplifiers. So we say that for this, a voltage divider circuit is used in the negative feedback loop, that is the connection to the negative input of the operational amplifier. Therefore, the Wien bridge is viewed as a non-inverting amplifier configuration with the input signal fed back from the output through the lead-lag circuit. Because the voltage divider determines the closed loop gain of the amplifier, we can now arrive at an equation that says that the closed loop gain is equal to 1 over beta. when we have said that the beta is the attenuation that takes place in the feedback loop. I say if we do that, it is equal to 1 over R2 over R1 plus R2, which is R1 plus R2 all over R2. Now, let's see the circuit we are talking about. This is a typical circuit of a Wien bridge oscillator. If you look at that, we say that there is a positive feedback that goes through the lead lag circuit. If you look at the lead lag circuit, which we have put in your shaded area, you see that you have the capacitors C1, C2, R3, R4. While in the negative feedback circuit, we have the voltage divider, which has R1 and R2. You can, read the circuit and see what is happening. In the feedback loop, when we say feedback or negative feedback loop now, we are talking of the input to the negative sign of the operational amplifier. You will see that it is not everything that is fed back through that voltage divider is fed into the negative input of the op amp, because some will go there, some will maybe escape through R2 to the ground. So, but the resultant voltage that appears there is what is fed into the negative part, whereas another signal or output is fed back through the RC network, which is called the lead lag circuit. Now, we will see what is happening at this lead lag circuit, because at certain point the signal continues to build up. When there is no phase shift again between the two lead lag circuits, the signal begins to decrease and the process repeats, giving rise to a signal that goes up, comes down, goes up, comes down, and that is the oscillation that is taking place. We see that illustration in this next question, which is question 5. We say, explain the condition for oscillation to occur in the Wien bridge. For the output to oscillate, we have known that the phase shift around the feedback loop must be equal to 0 degrees and the gain must be equal to unity. Now, this 0 phase shift condition is met when the frequency is at FR, that is the resonant frequency, because the phase shift through the lead lag circuit is 0 degrees and there is no inversion from the non-inverting input of the op amp to the output. We see that illustration. For the gain around the feedback loop to be unity, the closed loop gain of the feedback must be equal to 3. We will explain that further, because the attenuation of a typical feedback is 1/3 of the signal that comes through the lead lag circuit, thereby making the total gain around the positive feedback loop to be equal to 1. Like we've seen before, if this attenuation is 1/3, it means that the closed loop gain must be equal to 3, so that it will be AV times beta to be equal to 1 from the equation we had seen earlier. So 3 times 1/3 will be equal to 1. So when the attenuation continues to be 1/3 of the output and the gain of the amplifier is 3, it continues to nullify and the constant output of equal to 1 will be maintained. And we say that we reach this condition when the value of R1 is equal to 2R2. That is, the value of R1 in the divider network is equal to 2R2. Immediately you use that as your divider network resistances, then you will automatically achieve this feedback gain of 1 and phase shift of 0. That is what we illustrated. Loop gain equals 3. If you multiply it with the attenuation, which is 1/3 of it, it gives you an output. Go again to explain this lead lag circuit of the wind bridge, and that is what question 6 is asking us. Explain how the lead lag circuit of the wind bridge gives rise to response curve, that is the signal or the waveform that comes out of this wind bridge. So at some specified frequency, the response of the lead lag circuit will happen like this. The lag circuit takes over and the decreasing value of XC1, when we say XC1 is the reactance of capacitor 1, causes the output voltage to decrease. The response curve for the lead lag circuit is as shown in Fig 1b and indicates that the output voltage peaks at a frequency called the resonant frequency Fr. At this point, the attenuation, that is V out over V in, of the circuit is 1/3 if R1 is equal to R2 and XC1 is equal to XC2. So mathematically, V out over V in is equal to 1/3. See, the attenuation is the ratio of the output to the input. If you, by this mathematics here, it means that if you input 3 volts, what comes out is 1 volt. So the ratio V out over V in is equal to 1/3. The resonant frequency of the wind bridge is then given as Fr equals 1/2 pi RC, where R is the equivalent resistance of R1 and R2. If we look at the diagram we have above, that R1 and R2 will now be R3 and R4 when we drew the lead lag circuit. The R1 and R2 are the voltage divider network, but at the lead lag circuit, we used R3 and R4. So is the function of that R3 and R4, C1 and C2, that gives rise to this, because they are the resistors in the lead lag circuit. So the lead lag circuit in the Wien bridge oscillator has a resonant frequency of this, at which the phase shift occurs, and at that point an attenuation of 1/3, as we have seen. So let's look at this figure. This waveform written in blue, the vertical axis is the V out, the amplitude, the voltage output, while the horizontal axis is the frequency. At point 0, as the voltage is fed back, the lead circuit of the Wien bridge oscillator will continue, the reactance will continue to decrease. As it decreases with incoming voltage, then the output voltage continues to rise. It gets to the point where the reactance of XC1 is equal to the reactance of the XC2. At that point, the net phase shift will be equal to 0. So the voltage output, which is the signal, will have risen to the mark point where we are having FR. After that point, the reactance of the lag circuit takes over. When it takes over, the voltage continues to drop until it gets to the 0 level. Then at that point, the net phase shift between the lead and the lag circuit becomes 0 again. Then the lead circuit takes over again, and this signal will go up again, and the process continues to repeat itself, thereby giving rise to an output waveform which is uniform. So that is how the Wien bridge operates. Now, question 7 says, state 4 oscillators that use LC circuits for their oscillation. When we say LC circuit, you are talking of inductor capacitor circuit. Draw the circuit for the Colpitts oscillator and show the conditions for oscillation startup. So why are transistors used in LC feedback circuits instead of operational amplifiers? We quickly answer that the 4 oscillators that use LC circuits are the Clap oscillator, the Hartley oscillator, the Colpitts oscillator, the Armstrong oscillators, and the crystal controlled oscillators. Question B is, a typical circuit of the Colpitts oscillators using bipolar junction transistor as its amplifier. Remember, one of the questions is, why do we have to use bipolar transistors as amplifiers instead of op-amp? We answer that shortly. Then you see the tank circuit, or which we call the oscillating circuit, mapped in red. So how does this work? For oscillation to start up, the attenuation beta of the resonance circuit, that's that circuit marked in red, is basically determined by the values of C1 and C2 as shown in that figure. The voltage developed across C2 is the oscillator's output voltage, and the voltage developed across C1 is the feedback voltage. Voltage developed across C2 is the output voltage. You can see that it is the voltage going to the output that comes to C2, while the one, C1 going out from C1 is the one that is fed back to the transistor, which is the amplifier. So the expression for the attenuation is given as beta equals C2 over C1, which is the V out over VA. So for oscillation to be sustained, the voltage gain AV must be equal to 1 over beta. Therefore, AV will have to be C1 over C2. Simple mathematics, if beta is equal to C2 over C1, then 1 over beta will be equal to the inverse of that, C1 over C2, where AV is the voltage gain of the amplifier. So for the oscillation or for the oscillator to be self-starting, AV beta, that is the voltage gain times the attenuation, must be greater than 1. We have said it, for the thing to start, the output, the gain, must be greater than 1 until it gets to the point where it is stabilized at 1, so that the output is maintained at the same magnitude and periodic. So, this circuit shows us what happens, that the voltage gain must be slightly greater than C1 over C2 for oscillation to be self-starting. That is, AV must be greater than this. If you look at that, we have said that the voltage developed across C1 is the feedback, the one that goes back to the amplifier. We call that VF, whereas the voltage that comes into that tank circuit is the output voltage, which is equal to the one developed across C2. So it is now at this point that is self-starting. The first low voltage comes in at C2, something happens. At C1, something happens. And what happens in C1 is feedback. It comes out again and comes back to the tank circuit. And of course, the inductor there is helping to improve the reactance of what is happening at the tank circuit. So the signal continues to build up until such a time it will give what is required, and the voltage gain is designed that at that point the gain becomes equal to 1, so that a constant output is maintained. 8. Draw the equivalent circuit of a crystal and explain the action. We recall that we say that these relaxation circuits could also form crystal control oscillators. So, and it's one of the, LC oscillators. We can say that we use this diagram to show the equivalent circuit of a crystal. So it is an RC series parallel RC circuit. In one arm, you have RLC circuit in one arm in series. In the other arm, you have capacitive circuits, then two of them in parallel. We say that the equivalent circuit of a crystal is a series parallel RLC circuit. As can be seen, the crystal equivalent circuit is a series parallel RLC circuit and can operate in either series resonance or parallel resonance. At the series frequency, resonance frequency, the inductive reactance is cancelled by the reactance of CS. The remaining series resistor, RS, determines the impedance of the crystal. The parallel resistance occurs when the inductive reactance and the reactance of the parallel capacitance CP are equal. The parallel resonance frequency is usually at least 1 kHz, higher than the series resonance frequency. The great advantage of the crystal oscillator is that it exhibits a very high Q factor, high quality factor. Impedance of the crystal is minimum at series resonance, thereby providing maximum feedback. The crystal tuning capacitor C is used to fine-tune the oscillator frequency. Thank you for being part of this self-test 11. Look out for self-test 12. In that self-test 12, we'll be looking at the remaining part of our work, the multivibrators, the Schmitt triggers, and the field effect transistors. Thank you.